Space is the final frontier, a vast, mysterious realm that has fascinated humanity for centuries. From the enormous voids scattered across the cosmos to the very origins of time itself, the universe holds secrets that continue to challenge and inspire us. Join us as we journey through the mysteries of space, explore its past, witness its evolution, and look ahead to its future. If these science stories help you relax, a like or a subscribe will help others find this peaceful corner too. We often wonder if the universe has an edge, a boundary beyond which nothing exists. As we gaze into the cosmos, we realize our view is limited to what is called the observable universe, the part of space from which light has had time to reach us. Today, this visible universe extends 46.5 billion light-years in every direction. Even though the universe itself is only 13.8 billion years old, this difference exists because the universe is constantly expanding, stretching the distances between galaxies. Our vision is naturally limited by light. Light from distant objects can only reach us if it hasn't been blocked or stretched too far. This creates horizons in space. The particle horizon marks how far back we can see in time, while the event horizon defines the future distance from which light could ever reach us. Beyond these lies the Hubble horizon, where objects move away faster than light can travel, making them permanently invisible to us. So the universe may seem limited, but it is really our light-based perspective that is restricted. Even the light from nearby stars takes time to reach us. Sunlight travels 94 million miles in 8 minutes. Light from Proxima Centauri, our closest star beyond the Sun, takes 4.2 years to arrive. For distant galaxies, such as HD1, located 13.4 billion light-years away, observing them means looking far into the past. Light lets us study the early stages of the universe and understand how galaxies like our own formed. The study of light has led to remarkable discoveries. In the 20th century, astronomers Arno Penzias and Robert Wilson detected a faint, uniform glow from all directions. The cosmic microwave background, CMB. This radiation is the leftover light from the early universe created when atoms first formed 380,000 years after the Big Bang. Before that, the universe was too hot and dense for light to travel freely. The CMB, now cooled to -454 F, provides a snapshot of the young cosmos and a wealth of information about its composition, age, and evolution. By analyzing the CMB, scientists discovered patterns in temperature fluctuations that reveal how galaxies formed and evolved. These patterns also support the flat universe model and provide evidence for dark matter and dark energy, which together make up over 95% of the universe, 26.8% dark matter, and 68.3% dark energy. The CMB even helps estimate the universe's expansion rate, about 42 miles per hour per megaparsec, showing how space itself grows over time. Although our vision is limited by light, new tools allow us to explore further. Neutrinos, tiny particles that barely interact with matter, can travel immense distances at nearly the speed of light. They carry information from stellar processes, supernova, and other cosmic events, giving us insights beyond the visible universe. Similarly, gravitational waves, ripples in space-time caused by massive objects like colliding black holes, reveal events billions of light-years away. In 2016, scientists detected gravitational waves from a black hole collision 1.3 billion light-years away, opening a new way to study the cosmos. Despite these advances, the universe's expansion limits what we can see directly. Galaxies and stars are moving away from us, and many will eventually be beyond our observable horizon. The particle horizon itself grows as the universe expands, gradually revealing more objects, but many remain forever unreachable. Even the most brilliant cosmic events may never be seen by future observers. In the end, our understanding of the universe combines careful observation with clever techniques. From detecting ancient light to capturing invisible particles and waves, while there are limits to what we can see, science continually finds ways to push past them, bringing us closer to the secrets of the cosmos and helping us understand its past, present, and future. The expansion of the universe affects another key limit, the space event horizon. This horizon defines a boundary beyond which any signals, including light or radio waves, can never reach us. Today, its radius is about 16 billion light-years. That means even if a galaxy is within our particle horizon, if it lies beyond the event horizon, we can never interact with it. Signals sent from Earth now will stretch to frequencies we cannot detect, and the objects sending them will continue moving away. In the distant future, even galaxies we can currently reach may become unreachable. Another horizon, the Hubble horizon, lies about 14.5 billion light-years away. Beyond it, space expands faster than light, so objects there recede from us more quickly the farther away they are. Yet the Hubble horizon grows over time, allowing some distant light to eventually reach our telescopes. Eventually, though, it will shrink, leaving only our local group of galaxies visible. Around 10 billion years from now, the Hubble and event horizons will merge, creating a new boundary of 63 billion light-years, beyond which nothing will ever be observed. Over tens of billions of years, all light from beyond this horizon will vanish forever. Even with these cosmic limits, technology offers hope. Neutrinos, tiny particles with nearly zero mass, can travel vast distances, bringing information from distant events. Gravitational waves, ripples in space-time from colliding black holes and neutron stars, also allow us to study regions beyond our visible universe. Over time, advances in detecting these phenomena may help us expand knowledge even beyond our horizons. New particle horizons might eventually be established on other planets, extending humanity's reach further into space. Since the dawn of our species, humans have looked up at the stars, charting constellations, and wondering about the universe's boundaries. But we rarely consider the universe's final days, how time and existence itself will end. By traveling billions, even trillions of years into the future, we can explore the ultimate fate of the cosmos. We begin in the Anthropocene, our current era, marked by the significant impact of humans on Earth. Over the 11,700-year Holocene, humans developed agriculture, writing, and civilization. But our growth has left a mark. Climate patterns are shifting, extreme weather is increasing, and biodiversity is under threat. The Anthropocene shows the consequences of our actions and raises the question, what legacy will we leave? By the year 2500, Earth's magnetic poles will shift, disrupting technology. By 4385, Comet Halley returns, a reminder of cosmic cycles. By 5000, melting polar caps will have raised sea levels, submerging coastal towns. By 6000, a massive asteroid may collide with Earth, altering life dramatically. By 8000, distant stars will die in brilliant supernova, showing the universe's constant change. Fast forward 1 billion years, our sun brightens by 10%, making Earth hotter and destroying much of life. By 1.3 billion years, oceans evaporate, leaving Earth dry and barren. In 7.5 billion years, the sun becomes a red giant, consuming Earth. By 10 billion years, the sun collapses into a white dwarf, a dim remnant of its former glory. By 100 trillion years, stars begin to vanish, leaving the universe in darkness. By 1 quadrillion years, the universe cools further, becoming a vast cold void. White dwarfs fade into black dwarfs, marking the era of degeneration. Matter slowly disintegrates as protons decay, leaving only photons and neutrinos. Black holes emerge as the dominant objects. Supermassive black holes, formed from merging stars and smaller black holes, grow massive, absorbing matter and emitting gravitational waves, the final echoes of the cosmos. Even black holes are not eternal. Hawking radiation, proposed by physicist Stephen Hawking, slowly drains their mass, ensuring that eventually even these giants will vanish. The universe continues, expanding relentlessly. Space stretches, matter fades, and the familiar celestial objects disappear. Yet, even in darkness, the universe evolves. Gravity moves objects, occasionally sparking the birth of new stars, but over unimaginable time, light fades, and the cosmos becomes a silent, cold, and empty expanse. This is the ultimate fate of the universe. A quiet, dark cosmos where matter as we know it has vanished. Stars have died, and black holes have faded. Through it all, we've glimpsed the story of existence, from the first light to the final echoes of space and time. Black holes slowly disappear over time through a process called Hawking radiation. Near a black hole's edge, pairs of particles and antiparticles form. One particle falls in, while the other escapes into space, taking energy with it. Over billions of years, this causes the black hole to shrink, weakening its immense gravity until it eventually evaporates. These events mark the end of the last major objects in the universe, leaving behind an endless cosmic void. Since the Big Bang, the universe has been expanding, driven by dark energy. It's a mysterious force that counteracts gravity and speeds up cosmic expansion. At the same time, dark matter, which makes up about 85% of the universe's matter, pulls things together with gravity, balancing this expansion. Over time, the influence of dark matter could increase, possibly slowing or even reversing the expansion in a process known as the Great Contraction, collapsing the universe into an incredibly dense point, a singularity where space and time break down. From this singularity, a new Big Bang could potentially give birth to another universe, continuing the cosmic cycle. Our journey through time reminds us how brief human existence is compared to the universe's vast timeline. In a 100 million year span, the stars we see tonight will evolve. Massive stars will die, forming nebulae, while medium-sized stars like our Sun will grow slightly brighter by 1%. Over billions of years, humanity might reach advanced levels of stellar engineering, controlling star life cycles, replenishing fuel, and even influencing nuclear reactions. This could make currently uninhabitable planets suitable for life and provide nearly limitless energy using methods like the theoretical Dyson sphere. However, tampering with stars may also accelerate aging in nearby systems, creating risks. Galaxies, too, will change. Smaller galaxies will merge with larger ones, and over long periods, this will reshape galactic structures, possibly creating supermassive black holes. The Milky Way is moving toward Andromeda, though their collision is still about 5 billion years away. In 100 million years, galaxies in our local group will have shifted positions slightly, and faraway clusters like CLJ 1001 plus 0220 may become nearly invisible due to expansion. The universe itself continues to expand. Expansion doesn't mean matter moves on. It's its space itself that stretches. This causes galaxies to drift apart over time. Currently, the expansion rate is about 44 miles per hour per 3.26 million light-years, and it is accelerating due to dark energy. This increasing speed will eventually prevent new stars and galaxies from forming, scattering gas and dust and leading to the universe's heat death. There are other potential threats. Over billions of years, protons, the building blocks of atoms, may decay, destabilizing matter. While this wouldn't destroy the entire universe instantly, it could disrupt galactic evolution in affected regions. Another danger lies in a true vacuum bubble. If the universe shifts from a metastable to a true vacuum state, a bubble could expand at the speed of light, destroying all matter in its path and preventing any life from forming. Finally, in the distant future, black holes will vanish through Hawking radiation, leaving a universe dominated by cold, dark space. Stars will have died, galaxies will fade, and matter will slowly decay. Yet, despite these inevitable changes, humans will continue to explore, discover, and record the history of the universe. Even in the face of the universe's ultimate fate, curiosity and knowledge will endure. Space, the final frontier, remains a vast, mesmerizing expanse, a cosmic stage, where stars, galaxies, and nebulae reveal the story of existence, past and future, waiting for humanity to continue exploring. What happens when we discover a gap in the cosmic structure? A place so vast and empty that traveling at the speed of light would take more than 330 million years to cross about. It's 23 times the size of our Milky Way. These regions, known as cosmic voids, are not science fiction, they are real. It's mysterious spaces where galaxy density is strikingly low. The idea of cosmic voids dates back to early astronomy. In the 18th century, telescopes allowed astronomers to map the Milky Way, but they couldn't see structures beyond it. By the 20th century, modern telescopes revealed billions of galaxies, and astronomers noticed empty regions, first thought to be errors. By the 1970s and 80s, redshift studies showed that galaxies form a cosmic web, with clusters, filaments, and vast voids in between. Later, digital sky surveys and 2D redshift studies created detailed 3D maps. revealing these empty regions more clearly. Cosmic voids are integral to the universe's structure. Galaxies are not randomly scattered. They form networks with voids as large, empty spaces separating dense clusters. Some of the most famous voids include Bode's Void, discovered in 1981, with a diameter of about 330 million light-years. In this cosmic desert, only 60 galaxies exist where 10,000 would normally be expected. Another enormous void is the Eridana supervoid, stretching 1 billion light-years. It's linked to a cold spot in the cosmic microwave background through the Sachs-Wolf effect. Even larger is the Cons-Venetine supervoid, 1.2 billion light-years across, highlighting the sheer scale of emptiness in the universe. How did these voids form? Several ideas exist. Cosmic inflation after the Big Bang stretched space rapidly, amplifying tiny quantum fluctuations into denser and less dense regions. Gravity then pulled matter into clusters, leaving voids behind. Dark energy may also have pushed galaxies away from low-density regions, enlarging voids over time. Lastly, as matter clumped under gravity to form galaxies and clusters, voids naturally appeared in the leftover space, similar to bubbles and bread rising. Understanding voids is challenging because of the universe's complexity and the mysterious roles of dark matter and dark energy. Yet, studying voids provides key insights into the universe's evolution and tests cosmological models. Observing their size, shape, and distribution can confirm or challenge current theories. Some scientists even speculate that voids could hint at alternate universes. Certain interpretations of quantum mechanics and string theory suggest these empty regions might be interfaces with other dimensions or universes. While highly speculative and lacking direct evidence, this idea bridges the familiar universe with concepts beyond our current understanding. Quantum physics may also play a role in creating voids. In the earliest moments after the Big Bang, tiny quantum fluctuations could have expanded with the universe, forming regions of uneven density. Over billions of years, these less dense areas evolved into the voids we observe today, leaving a lasting imprint on the cosmic fabric. Cosmic voids remind us that the universe is far from uniform. They are vast, empty, and mysterious, but they also connect the largest structures in the universe with the smallest scales of quantum physics. Exploring them brings us closer to understanding the universe and our place within it. Another fascinating idea takes us into topology, the study of space and its properties. In the universe, topological defects are irregularities in space-time areas where the normal structure is disturbed. These defects may have formed during the inflationary period, just fractions of a second after the Big Bang. When the universe expanded extremely rapidly, tiny irregularities were stretched, potentially preventing matter from gathering in these areas, leaving behind the cosmic voids we observe today. To understand voids fully, we also need to consider black holes, especially primordial black holes. Unlike the ones formed from collapsing stars, these may have appeared shortly after the Big Bang, due to extreme density fluctuations. Some theories suggest cosmic voids could be filled with these hidden black holes. Though they don't emit much radiation, their gravity can clear surrounding matter, shaping the voids. Dark matter may also play a key role. It makes up roughly 85% of the universe's matter and forms filaments that link galaxies together. If these filaments collapse or break, they could leave behind vast empty spaces, creating the cosmic voids we see. Despite being empty, voids are far from unimportant. They hold vital clues about the structure of the universe, the behavior of dark matter, and the influence of dark energy. Exploring voids pushes us to rethink our understanding of the cosmos. Every discovery brings us closer to unraveling the universe's secrets. Looking back, about 13.8 billion years ago, the universe began with a singularity, giving rise to the Big Bang. But what came before? Did time exist? Some theories suggest our universe might be part of an endless cycle of expansion and contraction, the oscillating universe. Each cycle starts with a Big Bang, expands for billions of years, then contracts into a big crunch, eventually triggering a new Big Bang. Other theories expand even further. The multiverse theory proposes countless universes, each with its own physical laws. Our universe could be just one bubble in a vast cosmic foam. Some might precede ours, others follow, but we have no direct evidence yet. Meanwhile, physics is guided by two pillars: quantum mechanics, which describes the tiny world of particles, and general relativity, which describes the very large. These meet in extreme places like black holes or the Big Bang. One attempt to unify them is the no boundary proposal by Stephen Hawking and James Hartle. In this model, the universe has no edge or beginning. Space and time are finite but unbounded, like the surface of a sphere. Asking what came before the Big Bang is as meaningless as asking what is north of the North Pole. String theory offers another perspective. It suggests the universe's fundamental building blocks are vibrating one-dimensional strings, not particles. These strings can create all particles depending on their vibrations. Some versions suggest our universe emerged from the collision of two branes in a higher dimensional space, possibly creating new universes in the process. Finally, the quantum vacuum offers yet another explanation. In quantum mechanics, a vacuum isn't empty, it teems with particles and antiparticles that appear and vanish. The vacuum fluctuation model suggests our universe might have begun as a tiny bubble in this quantum vacuum, inflating rapidly into the cosmos we inhabit. While these theories, oscillating universe, multiverse, no boundary, string theory, vacuum fluctuations are all speculative, they offer fascinating ways to imagine the origins of our universe. They bridge the largest structures with the smallest scales, helping us explore questions about existence itself, even if we may never have complete answers. One intriguing idea combines quantum mechanics with cosmology, the Big Bounce theory. Instead of starting from a singularity where physics breaks down, this theory suggests our universe may have sprung from a previous contracting universe. Quantum effects prevent total collapse, allowing the universe to shrink to a very small size and then bounce back, expanding again what we observe as the Big Bang, like the oscillating universe theory. It envisions a universe with no true beginning or end, cycling endlessly through contraction and expansion. Quantum mechanics is central here, just as particles can tunnel through barriers. The universe might tunnel from contraction to expansion. Another fascinating possibility involves black holes. Normally, black holes form from collapsing massive stars, creating singularities where density becomes infinite. But some scientists speculate that singularities could be birthplaces for new universes. In this scenario, our universe could exist inside a black hole from a parent universe, with the Big Bang marking the formation of that singularity and our universe's expansion reflecting the black hole's growth. Loop quantum gravity, LQG, offers a similar approach. This theory treats space as composed of tiny discrete loops, rather than being continuous. Applied to cosmology, loop quantum cosmology LQC provides a detailed quantum picture of the universe's evolution, including a Big Bounce scenario. Instead of collapsing into a singularity, the universe reaches a minimum size where quantum gravitational effects counteract further contraction, then bounces and expands again. Each cycle could begin with such a quantum leap, linking our universe to a previous one via a quantum bridge, a transitional phase connecting contraction to expansion. LQC elegantly removes the singularity at the Big Bang and offers a way to merge quantum mechanics with gravity. Yet it still faces major challenges. We don't fully understand how this quantum bounce works, or how it fits with observable physics. Overall, these theories, Big Bounce, black hole universes, and loop quantum cosmology are highly speculative. None yet has direct experimental evidence, but each provides a fascinating way to imagine what might have come before the Big Bang. Every theory opens new questions, but the journey of exploring these ideas expands our understanding of the cosmos and keeps the search alive. At present, the answer remains unknown, but the pursuit itself is what drives discovery and deepens our grasp of the universe.